Hello, hello, hello. This is Nicholas. In this video, I'm going to be deriving some properties of the Laplace transform. Before I do that, I'm going to be deriving... No, I think I should derive the properties first, actually. They would be of use to us to derive the other two that I wanted to do. The two other ones that I didn't do that come up a lot are the Laplace transforms of e to the at times the sine of bt and the Laplace transforms, or Laplace transform of e to the at cosine of bt. And it turns out that if I know the Laplace transform of e to the at and I know the Laplace transform of sine bt, I can actually just get this whole Laplace transform. And that's what I'm going to be doing today. So let's start out with the first property. Let's say if the Laplace transform of f of t gives us some new function, and it'll be in terms of s, I'll call it capital F, then the Laplace transform of e to the at times f of t is going to be f of s minus a instead. So where there's an s, stick an s minus a instead and you'll get the same thing. And this is really, really easy to prove because this is an integral. It's the integral from 0 to infinity of e to the negative st times e to the at f of t dt, which is the integral from 0 to infinity of e to the, I don't know, well, how do I want to write it? I'll write it as negative s minus a. Yeah, that's how I want to write it, dt. And times f of t dt, and that right there is exactly f of s minus a. In other words, that's the Laplace transform. See, where there was an s, we just plugged in an s minus a. And that has a pretty, that might seem like a really obvious property, but it comes really in handy a lot. So, for example, if I wanted to use this property to show, say, I wanted to derive that Laplace transform right there. So, if I take the Laplace transform of e to the at times the sine of bt, then what that's saying is I can just take the Laplace transform of the sine of bt, and then wherever there's an s in that Laplace transform, just stick an s minus a in. So I know that that's the Laplace. What I'm saying, if I remember that the Laplace transform of the sine of bt, I think it's b over s squared plus b squared. The Laplace transform of sine. See, I did it up here. B over s squared plus b squared. So the sine of bt is b over s squared plus b squared. Then that means the Laplace transform of e to the at times the sine of bt is nothing but b over s minus a squared plus b squared. That's it. Where there was an s, I put an s minus a. And likewise, for the Laplace transform of the cosine of bt, that's s over s squared plus b squared. And so then that means the Laplace transform of e to the at times the cosine of bt is just s minus a over s minus a squared plus b squared. So really, if you know just the Laplace transform of e to the at, sine of bt, and cosine of bt, and the t to the n, you can get a lot of Laplace transforms from this basic property. Another common one that pops up is the Laplace transform of e to the at times t to the n. So just recall then that the Laplace transform of t to the n, that's n factorial over s to the n plus 1. So now we just replace the s with s minus a, and so that would imply that the Laplace transform of e to the at times t to the n is just n factorial over s minus a to the n plus 1. So you can derive that, and that, and this one, just like that, right off the bat. So the only four really that I have committed to memory is sine, cosine,